Numerical aperture. The aim of the experiment is to find the fiber acceptance angle and hence the numerical aperture of an optical fiber cable. Optical fiber can act as an optical waveguide that allows the transmission of optical information. An optical waveguide is a structure that guides a light wave by constraining it to travel along a certain desired path. If the transverse dimensions of the guide are much larger than the wavelength of the guided light, then we can explain how the optical waveguide works using geometrical optics and total internal reflection. Total internal reflection occurs when light is incident on a dielectric interface at an angle greater than the critical angle. The critical angle is that angle of incidence in denser medium for which angle of refraction becomes 90 degrees. This waveguiding principle is implemented in optical fiber by a core cladding structure. In optics, the numerical aperture of an optical system is a dimensionless number that characterizes the range of angles over which the system can accept or emit light. By incorporating index of refraction in its definition, numerical aperture has a property that it is constant for a beam as it goes from one material to another, provided there is no optical power at the interface. The exact definition of the term varies slightly between different areas of optics. Numerical aperture is commonly used in microscopy to describe the acceptance cone of an objective and hence its light gathering ability and resolution. In fiber optics, it is described by the cone of light accepted into the fiber or exiting it. Numerical aperture refers to the maximum angle at which the light is incident on the fiber so that it is total internally reflected and transmitted properly along the fiber. Optical fiber cable consists of a central core of refractive index N1 surrounded by a cladding of refractive index N2. Core has a greater refractive index than cladding, that is N1 greater than N2. Let Ne be the refractive index of the ambient medium. The dotted line represents the axis of optical fiber cable. Let us consider light entering into the OFC, undergoing refraction at the ambient medium core interface. If it strikes the core cladding interface at critical angle, the angle of refraction is 90 degrees. That is, the light grazes through the boundary of core and cladding, which is not usable for communication. Let us take this path as reference and consider another pathway between the axis and the reference path. Light entering will be striking at the core cladding interface will be incident at an angle greater than the critical angle. Hence, it undergoes total internal reflection. This light undergoes multiple total internal reflections and can make it to the other end of the fiber and is usable for communication. Let us consider another pathway beyond the reference path as shown. This cannot be used for communication as the light hits the core cladding interface at an angle less than the critical angle and hence refracts into the cladding. Therefore, it cannot be used for communication. From this, we can infer that for light wave to undergo total internal reflections and make it to the other end of the fiber, it has to enter in the fiber through paths between axis and the reference line. Similarly, by symmetry, we can consider another reference pathway as shown, which makes critical angle at the core cladding interface. Light has to enter into the OFC between the two reference pathways to undergo multiple total internal reflections so as to be useful for communication. This representational figure is in two-dimensional plane. When we consider the three-dimensional scenario, this triangular section forms a conical section. This conical section through which light has to enter into the OFC to undergo multiple total internal refractions is known as the acceptance cone of the OFC. This implies that there is a maximum value of angle of incidence at the core ambient medium interface beyond which it does not propagate, rather than it is refracted into the cladding. This maximum value of angle of incidence is known as the acceptance angle, represented by alpha m. The sign of acceptance angle is called the numerical aperture of the optical fiber cable. To find how the numerical aperture is related to the refractive index values of the OFC, let us consider light entering into the OFC such that angle of incidence at the core medium interface is the acceptance angle, so that light is incident at the critical angle in core cladding interface. Let the angle of refraction at the first interface be theta. Applying Snell's law of refraction in the ambient medium core interface, NA sin alpha m is equal to N1 sin theta. From the right triangle, theta plus c is 90 degree, hence the equation can be modified. NA sin alpha m is equal to N1 cos c, equation 1. Applying Snell's law again in the core cladding interface, N1 sin c is equal to N2 sin 90. Rearranging, sin c is equal to N2 by N1, or cos c, which is root of 1 minus sin square c, can be written as root of 1 minus N2 square by N1 square. This forms equation 2. Using equation 2 in equation 1, we have Na sin alpha m is equal to N1 root of 1 minus N2 square by N1 square. On rearranging, sin alpha m is equal to root of N1 square minus N2 square divided by Na, where Na is the refractive index of the ambient medium, N1 and N2 are the refractive indices of core and cladding respectively. The numerical aperture is given by sign of acceptance angle. If the ambient medium is air, Na equal to 1, hence numerical aperture is root of N1 square minus N2 square. Today's world rely on fiber optic cables for much of the data transmission. Information from various points is transmitted digitally using pulses of light via fiber optics cable, eventually reaching a destination thousands of kilometers away from the source. Fiber optic lines are thin, flexible, transparent strands of optically pure silica glass or plastic used to transport digital data via a light source. These strands are typically smaller in diameter than a human hair. A fiber optic strand consists of multiple layers. The actual conductor is a silica glass or plastic core. This core is surrounded by a refractive coating called cladding, which provides a reflective surface and causes the light to travel along the entire length of the core. The third layer is a buffer coating to protect against moisture and other damage. It also prevents light from escaping the strand and may have a color coding for identification purposes. Fiber optic strands are typically bundled into a cable. Fiber specifications list the core and cladding diameters as a ratio. Multimode fiber is usually either 62.5 by 125 microns or 50 by 125 microns. Single mode fiber is commonly 9 by 125 microns. Fiber optic cables have many advantages over copper cable, including immunity to electromagnetic interference. They are smaller and lighter than copper. They are capable of greater transmission distance and higher bandwidth and have less signal degradation. The greatest advantage is their ability to carry digital information over long distances at significantly higher rates than copper. The ability of a fiber optic strand to transmit data is based on the optical phenomena of total internal reflection. Light waves have three primary properties that affect total internal reflection. These are reflection, refraction, and refractive index. Here we see a light wave as it propagates straight through two different mediums. The speed of light waves changes depending upon the medium through which it passes. Medium A and medium B each have a different refractive index designated by a lowercase n. Medium B with slower moving light wave has a higher refractive index than medium A. For example, water has a higher refractive index than air. A wave propagating through water will travel at a slower speed than the same wave in air. The boundary or interface between the two mediums is where the refraction and reflection occur. Refraction is the bending of light wave as it passes from one medium to the next. If the second medium prevents light from passing through the interface, reflection occurs. Two factors must be considered when determining the degree of refraction or reflection: the angle at which the light wave strikes the interface and the refractive index of one medium in relation to the other. Snell's law is used to determine the amount of refraction that will occur between two mediums. Imagine a line perpendicular to the interface. This line is referred to as normal. A light wave traveling straight into the new medium or along the normal will change speed but not change the direction. However, when the light hits the interface at an angle, the change in light speed will cause the beam to change direction and propagate through the second medium at a different angle. The angle at which light hits the interface is referred to as angle of incidence. The angle at which the light propagates through the new medium is called the angle of refraction. By placing the known values into Snell's formula, the degree of refraction can be determined. Snell's law states that if the refractive index of the second medium is greater than that of the first, the angle of refraction is smaller than the angle of incident, and conversely, the refractive index of the second medium is smaller than that of the first, the angle of refraction is greater than the angle of incidence. This is the principle that enables light to travel through a fiber optic strand. The core has a higher refractive index than the surrounding cladding. A light wave from the core will increase in speed when it enters the cladding, which has a lower refractive index. Notice that as the angle of incidence becomes greater, the angle of refraction approaches the boundary or interface. If the angle of incidence is such that the refracted light wave travels along the boundary between the core and cladding, it is known as critical angle. If the striking angle or angle of incidence is greater than the critical angle, the light will be reflected with no refraction. This is known as total internal reflection. In general, the fiber optic communication system consists of a transmitter to produce and encode the light signals, optical fiber to conduct the light signals, and an optical receiver at the destination to decode the light pulses and return them to digital form. The electrical signals can be either digital or analog. Analog signals also require use of a pulse code modulation to convert them to digital form. The transmitter is composed of an interface circuit, source drive circuit, and the optical source. The interface circuit processes the electrical signal, making it compatible with the source drive circuit. In turn, the source drive circuit varies the current to modulate the optical signal. Finally, the optical source changes the electrical energy into light. The pulses of light are sent through the transparent core of the cable. The receiver consists of a photodetector, an amplifier, and a signal restorer. The photodetector transforms light pulses into electrical signals. It is light sensitive and must be capable of detecting even weak light pulses. The amplifier increases the signals received from the photodetector. This is the primary source of electrical noise in the receiver, and the sensitivity of the receiver is dependent on minimizing this noise. Lastly, the signal restorer converts the amplified electrical signal into a form that is suitable for the interfacing circuitry. Quality transmitters and receivers work together to ensure less signal degradation across the network. However, long-distance applications also require the use of either repeaters or optical regenerators to boost the light signal. A repeater converts the light signal back into an electrical signal and then regenerates a new optical signal. A fiber optic repeater cannot distinguish between pulses of light that are of different wavelengths and is less effective with multimode fibers. An optical regenerator uses a laser to optically amplify the signal. These are able to boost the strength of individual wavelengths of light and are appropriate with either single mode or multimode fibers. Another device that may be added within the system is an optical coupler or beam splitter. This is used when necessary to channel signals to multiple locations. Splitters are distinguished by numbers that represent the percentage of signal divisions. For example, 60-40 or 80-20. The cable used within the optical fiber communication system requires different types of strands depending on the usage. Fiber strands differ depending on the design of the core in relationship to the surrounding cladding. Depending on the type of light source used, the light waves propagating through the core may follow a variety of paths. A mode describes the path of a light wave as it travels through the core. The mode or path is determined by the angle of the light entering the strand and the refractive index of the cladding. If the angle of the entering light wave is too sharp, the wave will not propagate through the cable. There are single mode and multimode fiber optic strands. Both single mode and multimode fibers are typically 125 microns in outside diameter, but the core is significantly smaller in a single mode fiber. Single mode fibers are approximately 5 to 10 microns in diameter. A single mode fiber strand is so minute that it allows a focused laser light entering the core to stay at an angle of 0 degrees without any loss into the cladding. Therefore, the bandwidth is almost infinite. It is commonly used to send data over great distances and at high speed. Multimode fiber has a large core diameter of 50 to 100 microns. The most commonly used sizes are 50 or 62.5 microns in diameter. Multimode fiber can use either laser or LED light sources. The large numerical aperture allows light waves to enter the core at a variety of angles. If the light wave enters the core at an angle close to 0 degrees, it is referred to as having a lower order mode. As the entering light wave deviates from 0 degrees, the order of the mode increases. The higher the order of the mode, the more the light wave will strike the cladding as it moves down the core. Consequently, a higher order mode takes longer to reach its destination. This timing difference between higher and lower modes creates modal dispersion and degrades system performance. As a result, multimode fiber strands are mostly used for data transmission over shorter distances. Multimode graded index fibers were developed to address the problem of modal dispersion. Graded index fibers have their highest refractive index at the center of the core. The refractive index of the core declines gradually so that the value at the outer edge of the core equals the refractive index of the cladding. The higher the refractive index of a medium, the slower the light waves will travel. Therefore, this design reduces modal dispersion by allowing light waves in the outer regions of the core to travel faster than those in the center of the core, causing them to reach their destination simultaneously. This reduces signal loss. Historically, single-mode, multimode, and multimode graded index fiber strands were made of glass. Now, plastic optical fibers have been developed that offer the same effectiveness as glass multimode fibers. Plastic optical fiber is much less difficult to install and maintain, making it preferable in many situations. In this experiment, we use a screen projection method to estimate the fiber acceptance angle alpha m. This depends on the fact that the acceptance angle at the entrance of the optical fiber is equivalent to the angle of exit of the fiber. The emergence cone of the optical fiber on projecting to a plane surface develops a trace with a disc shape. Let the trace be made at a distance L from the tail of the optical fiber. The radius of the disc be r. From the geometry, sin alpha m is opposite side by hypotenuse and is given by r divided by root of r square plus L square. Using r is equal to d by 2, we have numerical aperture is equal to d over square root of d square plus 4l square. Procedure. With the experimental setup, we launch the laser into the optical fiber. For launching laser into the optical fiber, we have a convex lens which will direct the laser into the optical fiber. This is called coupling. If the launched light is well within the acceptance angle of the fiber, it gets guided by multiple total internal reflection. Assuming the OFC to be lossless, that is short length, the entrance angle will be the same as that of the emergent angle. Diameter d of the spot and the distance between the screen and the fiber are measured. The light leaving the OFC is made to fall on a screen. The light falling on the screen will create a circular spot on the screen arranged at a distance L from the other end of the fiber. This is repeated for different values of L, and the arithmetic mean of the value obtained is the result.